So we're in chapter 12. Last time we talked about solids, liquids, and gases again. We touched on some of these ideas like surface tension for liquids. We also talked about viscosity. And this was really stuff that we'd kind of covered already. Also, feel free to put questions into the Zoom chat if you want. Oh, I meant to set these to everybody, just in case anybody couldn't get on. Or, of course, you can always speak up. Do my sniffles over there. Okay, yeah, so you can always speak up if you want and ask questions. That's fine. I'll try to be good about checking the Zoom chat. But we talked about viscosity, which is this resistance to flow for liquids. Basically, the stickier, the thicker a liquid is, the more viscous it is. And that has to do with the intermolecular forces. I don't know why I'm holding this up. I have a second. Has to do with the intermolecular forces between molecules. So if we have stronger intermolecular forces, which again is the whole theme of this chapter, if we have stronger intermolecular forces, then we'll have a more viscous liquid. So oil is more viscous because there are stronger intermolecular forces than water, per se, or than something like acetone, nail polish remover. It's probably the least viscous liquid that most of us are familiar with. So these are going to be very, in terms of, what I'm expecting you to know for these, is going to be very conceptual type questions. More of our focus will be on some of the math that comes later. So moving on from that, though, those properties of liquids, we're going to talk about evaporation and condensation. So evaporation or vaporization are physical changes in which a substance is converted from its liquid state into a gaseous state. Pretty familiar with that one. The rate of vaporization increases with increasing surface area, increasing temperature, and decreasing strength of intermolecular forces. So I think the easiest one, the most relatable one, is increasing temperature. If you spill water on the ground in the summer, it's going to vaporize very quickly because it's hot. If you spill water, outside on the sidewalk in the winter, it stays there for a long time, which is kind of why, aside from there actually being rain in the winter, around here everything looking wet. Because that lower temperature means that water is evaporating more slowly. Similarly, if you wash pans and you're too lazy to grab a towel to wipe it off, you can just put it on the stove and heat it up and evaporate that water quickly. But this is also related to these intermolecular forces, and really everything is going to come back to these intermolecular forces. So liquids that evaporate easily are termed volatile, while those that do not vaporize easily are non-volatile, right? Non meaning not. In the process of evaporation, molecules on the surface of a liquid are held less tightly than those in the interior, right? Because those on the surface have one side that's not touching the liquid, whereas those on the interior are surrounded by the other molecules of that liquid. So the most energetic molecules on that surface can break away into the gas state in a process called evaporation. So this is why, and I didn't talk about this one before, but increasing surface area also increases evaporation because you have more molecules that are on the surface that are being held less tightly and might have enough energy to leave the liquid. For any given, really for the temperature of anything, the sample of molecules or atoms will have a distribution of kinetic energies. And I wish I had thought to bring up the model from last week, or from 2 weeks ago, right? We were looking at that model on, I guess it's PHET, P-H-E-T. It's a molecular simulation website. Because you can see there that there are some molecules that are moving fast in that simulation, and there's some that are moving slow, which is what this graph is showing. So we take a look at this graph. This is essentially the fraction of molecules So how many molecules? So you could say, like, here there's 100 molecules that are moving at that speed because this is a kinetic energy. So more kinetic energy means more speed. So the higher that this curve is, the more molecules that are moving at that speed or have that amount of energy. So for any substance, we're going to have a whole range of energies of the particles. And when you heat something up, you're taking that curve and going from this red, or well, I guess I'm writing with red, but you're going from this lower temperature, the blue curve, to the higher temperature, the red curve. And then this dashed line is representing our minimum kinetic energy needed to escape the liquid. So some proportion in the blue curve here has enough energy to leave. But if we heat things up and we shift our curve over, we end up getting more particles that have that required kinetic energy. So that's how temperature is really one of the ways that temperature affects how fast something evaporates, increasing that proportion with enough energy. Condensation, on the other hand, is the opposite of evaporation. So it's a physical change in which a substance is converted from its gaseous state. So we're going from something like steam into a liquid. Evaporation and condensation are opposites. When the rates of condensation, and this is an important one that'll actually come into play in chapter 15, when the rates of condensation and evaporation become equal, a dynamic equilibrium is reached and the number of gaseous water molecules above the liquid remains constant. So you can imagine if you had two buckets of, I don't know, marbles. Here, I guess I could draw something. So we've got two buckets, expertly drawn buckets of marbles. And we have two people who are moving marbles between the two buckets. So as somebody pulls one marble over here, the other person is putting a marble back over there. And so if you're swapping those marbles at the same rate, then the number of marbles in each bucket stays the same. There are some things that can affect this when we're talking about liquids evaporating and condensing. And then, but we'll talk about that, I think, in the next slide. The vapor pressure, another property of liquids, is the partial pressure of a liquid's vapor in dynamic equilibrium with its liquid. So if you remember back to the hydrogen lab, which I know is pre-spring break, and nothing before spring break has remained in your minds. But if you think back to that, we had to figure out the vapor pressure of water so that we could calculate the vapor pressure of our hydrogen that we collected. Because we had, and I'll draw another picture here, we had our eudiometer, which was upside down, and the beaker of water. And then this thing was full of water up to a certain point. And so there were some water molecules in that space that we had in the eudiometer. And that vapor pressure, conveniently there, that vapor pressure is dependent on the temperature of the water. So we could figure out what that vapor pressure was, and we could figure out how much of the pressure in this headspace, is what it's called, in this headspace that we had, was due to water, and how much was due to our hydrogen, since our hydrogen would be the rest of it. And if you want to go back and look that up, that was Dalton's law of partial pressures. Excuse me. Again, sorry for the sniffling. Okay, so if our condensation and our evaporation are equal, that's a dynamic equilibrium, and that is also where we get the vapor pressure from for any liquid. So part of the reason that this happens, part of the reason we can get to a dynamic equilibrium, is because when we first start with our evaporation, these water molecules leave. As more and more water molecules leave, they enter into this headspace. But that also means that there are more and more water molecules that are coming back in contact with the liquid and might get stuck again. and thereby return to the liquid. So we can reach a certain point where there are enough water molecules above the water coming into contact with the surface of the water that the rate of them getting stuck is the same as the rate of them leaving the liquid. And that's where we're getting our dynamic equilibrium. So we can increase vapor pressure in a couple ways. One is increasing temperature. That's the one that we use to determine the vapor pressure of water in our hydrogen lab. And then this is one that we didn't have any control over. But vapor pressure also increases with the decreasing strength of intermolecular forces. So as those molecules do a worse and worse job of sticking together, it's easier for them to leave the liquid and go into the gas phase. So our vapor pressure, our vapor pressure though is independent of surface area. So we talked about, I'll go back here a couple slides. Right, vapor pressure, the rate of vaporization, it increases with surface area, temperature, and decreasing strength. But vapor pressure does not increase or change at all with an increase or decrease of surface area. So if our surface area remains the same, or if our surface area changes, let's say it gets bigger, if we increase our surface area, then we increase the rate of evaporation, but we also increase the rate of condensation, because now there's more area for our water molecules to stick back to the liquid. So let me know if there are any questions. So our boiling point, boiling is related to vapor pressure. So again, vapor pressure goes up as temperature goes up. Sorry. Vapor pressure goes up as our temperature goes up. And then at a certain point, our boiling point, there's enough thermal energy from our increased temperature to cause the water molecules on the interior of the liquid to become gaseous, which forms bubbles containing our gaseous water molecules. So when you see water boiling in a pan, those are groups of water molecules that suddenly have enough energy to unstick from each other and become a gas in the middle of the liquid. So a roiling boil is caused by all of those water molecules suddenly becoming gas. And again, that's because our temperature, we've reached this temperature at which our vapor pressure is equal to the pressure above it, or atmospheric pressure. One of the interesting things about boiling that I think is maybe lesser known is that when you reach boiling point, once the boiling point of a liquid is reached, additional heating only causes more rapid boiling. It does not raise the temperature of the liquid above the boiling point. So if you get water, right, boiling water and steam at a temperature of 100 degrees C will always be 100 degrees C at 1 atmosphere of pressure. That's a caveat there. And then only after all of the water has been converted to steam can the temperature of the steam rise beyond 100 degrees C. So this is key at 1 atmosphere of pressure, because remember, our vapor pressure, or boiling point, I should say, is when the vapor pressure equals the atmospheric pressure, or the pressure above the liquid. So this is why if you boil water to make pasta, here, it takes, spaghetti is like 10, 11 minutes. If you go, all the way up to China Peak and you try to boil water up there to make pasta, your pasta is going to take a lot longer. Or maybe not a lot longer, but it's going to take longer because the temperature that it takes to get to boiling is going to be lower. So you might boil at something like 95 degrees C instead of 100. So you're going to need longer to fully cook your pasta. Because at higher elevation, the atmospheric pressure is going to be lower. All right, so when it comes to sort of looking at this data, we get a very distinct curve that we can graph. So we have, on this graph, we have heat added as our x-axis. So as we're going from left to right, that's more and more and more heat that's been added to our water. So it's leaving our pot of water on the stove to boil. And then the temperature of the water here is our y-axis, right? So as we go higher, higher temperatures. So if we're boiling water, this is why, well, water takes a long time to boil because it can absorb a lot of heat, but it takes a long time to get all the way up to 100 degrees C. So, right, this is all heat being added all the way up until this point. We're just adding heat, adding heat, adding heat, and our temperature is going up and up and up until we get to 100 degrees C. At that point, our temperature stops raising. And the only thing that happens is our water is going from water to steam. And then at this point, you see here, we're still adding more energy. Right? This takes an amount of energy to get, to boil it all off. And only after that point can we take that water or take the steam now, all the water's gone, and increase the temperature again beyond 100 degrees C. So evaporation or vaporization is an endothermic process. So our system absorbs heat because energy is required to break molecules away from the liquid. Again, remember, we've got all these water molecules in here together, and they have these intermolecular forces. And just like, you know, stretching a rubber band until it breaks, or even ripping paper, right? Something like that takes energy to break that. You're breaking bonds, either in the rubber band or in the piece of paper, or if you're ripping things, pulling things apart, that all takes energy. And these bonds, these intermolecular forces, are no different. So we need extra energy to pull those apart rather than make them move faster. And so that means our system is, or evaporation is endothermic. And I think the thing that always helps me with this is to think of our system. This is our water. So to break bonds, it takes energy. So we're putting energy into the system, which means it's endothermic. So energy goes into the system, right? It takes energy to heat water to boil it. That's an endothermic process. And this is actually how our bodies, this is why we sweat, right? Our bodies use the endothermic nature of evaporation for cooling. As the sweat evaporates, it absorbs heat from our bodies to become a gas, and it cools us down. This is how swamp coolers work, if you have one of those. Basically have a mesh that's wet, and you blow air through it. As the water evaporates, it cools the air down. But it only works to a certain point, and it only works with a certain amount of humidity. Because if you have high humidity slows down evaporation and prevents cooling. So if you are ever in a hot environment, it's easier to get heat stroke than it is in a dry environment. Not that both aren't possible. Or heat exhaustion. Okay, so evaporation, endothermic. Condensation, the opposite process, is exothermic. So heat is released when a gas condenses to a liquid. As steam condenses to a liquid on your skin, it releases heat, causing a severe burn. So in addition to the steam being hot and making your skin hot, when it hits your skin, which is cooler than the steam, it also condenses, and now it's forming new bonds and releasing more energy, and causes a more severe burn than just spilling hot water on yourself. So the exothermic nature of condensation is also the reason that overnight temperatures do not get as low when humidity is higher. So if there's a lot of moisture in the air, as it cools off at night, that moisture is going to start to condense on all of the surfaces, blades of grass, buildings, everything as it cools down, and release that heat energy. So it prevents things from cooling off. Generally here, things cool off, at least as long as it's not overcast at night because it's so dry. Of course, then the opposite happens in the morning as things start to warm up. All of that dew starts to evaporate again, which absorbs heat, overall sort of leveling out the temperature. So you don't get as wide temperature swings. So we can put numbers to these things too, though. And the math here is not super difficult. Our heat of vaporization, or delta H vape, is the amount of heat required to vaporize 1 mole of liquid. So this is going to be in units of kilojoules per mole. So the heat of vaporization of water at its normal boiling point is 100 degrees C, or 40.7 kilojoules per mole. So if you have 1 mole of water, so if we have 1 mole H2O, we can multiply that by 40.7 kilojoules per mole and get 40.7 kilojoules as the amount of energy that's released. So if you have 2 moles, then you double that, right? So it would be 2 moles H2O times 40.7. And delta H here, this is maybe the one thing that can get a little bit tricky about this. Our delta H is positive because vaporization is endothermic. And it's positive also because we're adding 40.7 kilojoules of energy to the water to make it boil if we have 1 mole of water. Right? Our energy must be added to the water to vaporize it. So that's our heat of vaporization. And then the exact same amount of heat is involved when 1 mole of gas condenses, but heat is emitted rather than absorbed, right? Because vaporization is endothermic. Not evaporation. Condensation is exothermic. So they're opposites. So if we're going from here, again, this G means gas. So we're going from water, gas, to water, L is liquid. We're reversing that number from our previous slide here, where we had a positive 40.7 kilojoules. Now we have a negative 40.7 kilojoules. So our delta H is negative because condensation is exothermic. Energy is given off as the water condenses. So we can use this heat of vaporization to calculate actually the amount of energy that's needed to vaporize a given amount of liquid. So if you know that you've got a liter of liquid, you can figure out using this math how much energy that liquid's going to take to boil or to be completely turned into gas. So you can use the heat of vaporization as a conversion factor between the moles of liquid and the amount of heat required to vaporize it. Again, this is why, harped on unit conversions at the beginning so much. They continue to just be very, very important for all the things that we're doing. And we've talked about, the volatility of different liquids. So if something is more volatile, then easily turns into a gas. If it's less volatile or non-volatile, then it doesn't easily turn into a gas. And this is related to the strength of those intermolecular forces. So water here, right, H2O, has a normal boiling point of 100 degrees C. Our heat of vaporization is 40.7 kilojoules per mole. And notice we do have another one here. So if at room temperature you were to vaporize water without heating it up, this is like leaving a glass of water out or leaving a dish of water out. And it's slowly evaporating at room temperature. That requires a different amount of energy. It's actually more energy. I didn't actually prepare a Mentimeter quiz for this, but let me try. We can do one on Zoom. Okay, so based on this graph, though, based on this table, if water has a normal boiling point of 100 degrees C, and let's just compare it to isopropyl alcohol. So which has stronger... Which one has stronger intermolecular forces? So our choice one here is going to be water, and then, what is it, isopropyl. Isopropyl alcohol. So I can launch that. So which of these has stronger intermolecular forces? Just based on the boiling point heat of vaporization. If there's a question, I'm not going to expect you to memorize specific boiling points. I don't anticipate giving you this on an exam. Giving you this table on an exam. We'll go over some ways a little later in the chapter for how you can do that. All right, so I got 5 people who have responded. 6. Okay. More people voting for isopropyl alcohol. Remember, we're looking for the stronger intermolecular force. I guess we can cut it off there. Remember, these are anonymous, so if you get it wrong, it's fine. This will help me, though, determine if we need to talk about things more. And at this point, we haven't really discussed this very much, but okay. So I'll cut that off. I don't know if you guys can. Okay, I guess now you can see the results. I don't know if you could see them while it was going. So we had 62% voted for water having these stronger intermolecular forces, and then 38% voted for isopropyl alcohol. So in this case, it is the water that has the stronger intermolecular forces. And the way that you could know that here is because it takes more energy to break those bonds. Because remember, when we're going from a liquid to a gas, we need to break the bonds of the liquid to turn it into a gas, right? Because gases don't have those intermolecular forces. So then out of all of these, right, diethyl ether has the lowest boiling point. It also requires the smallest amount of energy to vaporize. And therefore it has the weakest intermolecular forces. But we'll talk more about those. It's just kind of like a hint at what's to come, I suppose. Woo, finally get to do some math. Okay, so calculate the amount of heat in kilojoules. Really recommend always underlining whenever just units are given in any question, just underline those units. It can save you some grief. Did not want to do that. Okay, so calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. The heat of vaporization is 40.7 kilojoules per mole. So that is the kind of thing that I would give you. I'll either give you a table of heats of vaporization, or I will just give you the specific number that you need to use. Okay, so we've got 2.58 kilograms of water. And we know its heat of vaporization is 40.7 kilojoules per mole. So when I look at this, looking at this problem, I think your first instinct should be we have an amount of water, and the amount of energy that it's going to take to heat up that water is dependent on how much water we have. But we can only do this in units of moles. So if we have our mass of water, we want to convert that into moles of water. So 2.58 kilograms of H2O. And we know that water is 18.02 grams per mole. So we need to convert actually our kilograms here into grams. So we're going to do 2.58, and then there are 1,000. So the units I want are grams, so I'm going to put that on top. And there's 1,000 grams per 1 kilogram. So that will give us grams of water. And then the units I want here is moles. So 1 mole of H2O. And then that's going to be 18.02 grams of H2O. So that will give us our amount of water in moles. And then we can just use our heat of vaporization, 40.7 kilojoules per 1 mole of H2O. So solving for that should give us the amount of energy in kilojoules. We get 2.58 times 1,000 times 40.7 divided by 18.02. So that's going to be, shift this whole thing over, 5,827. We do only have 3 sig figs here. This is kilojoules. So with correct sig figs, we need to use scientific notation. So it's going to be 5.83 times 10 to the 3 kilojoules. Whew. Are there any questions there? Going from, you mean, which part here? Oh, yes. Right. Sorry, yeah. Yeah, that's just the molar mass. So it's a molar mass of water plus the molar mass of 2 hydrogen atoms. And we'll have on Wednesday, I think Wednesday we'll have a little mini quiz. I might just do it on Canvas, but I'm hesitant to do that because it's too easy to cheat. Like I mentioned before spring break, little mini quizzes to go over old stuff. So I'm thinking nomenclature is going to be the first thing. And it'll just be a couple problems. Just a couple problems. Okay. Let's move on then, because we got a lot to cover. So this is a little bit of a more complicated problem. We have a drop of water weighing 0.48 grams, condenses on a surface. So we got water, 0.48 grams, condenses on the surface of a 55-gram block of aluminum that is initially at 25 degrees C. If the heat released during condensation goes only toward heating the metal, what is the final temperature in Celsius of the metal block? Specific heat capacity of aluminum we're given here is this. So this problem, I know, can be very intimidating. And I think the best way to approach it is to sort of sort out the things that are happening. This is a A-level question, by the way, that I would give on an exam, because it's requiring you to remember Q equals MC delta T, and combine that with our new heat of vaporization calculation. So we have water, sorry, we're going to need this heat of vaporization of water, which is 44.0. So heat of vaporization of water is 44.0 kilojoules per mole, equals delta H. So basically what we have happening here is a transfer of heat. All right, we have, oh, and I can use colors because you guys can actually see them. So I want to do it real small over here. So we have our water droplet, and that lands on our metal block. And that metal block weighs 55 grams, and our water droplet is, 0.48 grams. Right, let's see. Yeah, a drop of water condenses. So that's one of our key things here too, right? So this is really water vapor, and it's coming together to condense on our metal block. So condensation is exothermic. So is our metal block going to get warmer or colder? I want to do a poll here. Okay, so is the block going to get warmer or is it going to get colder if our little water droplet is exothermic? Are you guys able to change your votes if you wanted to? I'm not sure. I have not used the Zoom polls very much. Just curious. Okay. Good to know. All right, decently split here. Can you see the poll? Can you see the answer until I share it with you? Or sort of like what everybody's voted on? Okay. So I think I have to end the poll for those to be visible. That's most everybody, though. There's just, we got 21. So there's 3 people who haven't responded. That's okay. All right, so we got 61% for warmer, 39% for colder. We got this split in the class. Okay, so if our water droplet is exothermic, because it's condensing, and the water droplet is our system, that means heat is leaving that water droplet system and going into the metal block. So in this case, our metal block is actually warming up. Oh, I didn't show the results. It's 6139. So our metal block here is warming up because, again, you got to think of, what is the system here? What is exothermic? Which part is endothermic? That kind of thing. So our metal block here is going to be warming up, and we can use the math to figure out how much it's warming up by. We can use these 2 equations that, well, we really have one equation and then one conversion factor. So we have this Q equals MC delta T. Q is an amount of energy. M is going to be the mass of whatever we're trying to figure out if it's, or we're figuring out the final temperature of something, in this case the metal block, so it's going to be the mass of our metal block. C is our specific heat capacity, so that's this one. And then delta T, and I know it's been, again, pre-spring break, but delta T is our T final minus T initial. So if we know the amount of heat that went into the metal block, then we can use this equation to find that final temperature, because we were given the mass of the block, we're given the specific heat of aluminum, and we're given the starting temperature. And we can find the amount of energy that went into the block because we were given the mass of the water that condenses. So this problem is going to start out very similar to the last one. We're going to have 0.48 grams of water. So this is our water droplet. And then we need to convert that into moles. So again, we're going to use the molar mass. 18.02 is the molar mass of water, and that's grams per mole, so we want the moles. And that's going to give us, oh sorry, not done there yet, because we want to know how much heat is coming from that, so our delta H of vaporization is 44.0 kilojoules per 1 mole of water. So we do 0.48 times 44 divided by 18.02. And that'll give us, sorry, 1.17. There's more digits here, but that's kilojoules. Okay. We got 1.17 kilojoules, and of course we don't want to round anything until the very end. But now this is the amount of heat that has been released by our water condensing. And so we can go over to our Q equals MC delta T equation here and plug this in now. Let me move this over a little bit. So our Q is going to be our 1.17. Oh, sorry. Before we do that, that's in kilojoules. And our C here is just in joules. So we have to convert this from kilojoules into joules to make our units compatible, right? So that they'll work together. So when you're converting from, joules to kilojoules or back, or kilometers to meters or back, or kilograms, we're going to just move that decimal place. So in this case, we're moving the decimal place 3 places to the right. So this is going to be 1,172. I got the 2 from my calculator. Sorry, not kilojoules, that's joules. And so our 1,172 joules be equal to the mass of the metal block, which is 55 grams, times 0.903, and that's in joules per gram degree C. There's going to be times our T final minus our T initial, which is 25 degrees C. And then we can just do some algebra to solve here. So let's do the 55 times 0.903. And that's going to be 49.665 times, I'm going to leave these in parentheses. And so then we'll take our 1,172, divide it by that 49.665. So this is now 23.5987. And that's going to equal T final minus 25 degrees C. So we add 25 to both sides. Plus 25. And our final temperature here is going to be 48. How many sig figs? I think just 2 sig figs. Sorry, so 49 degrees C equals our temperature final. Yes. Are there any questions on that one? I know that's a tricky one. Yeah. Mm-hmm.
No. Or energy, I mean.
We used Q equals MC delta T to find the final temperature.
Oh, the final temperature. Okay.
Yeah, so we used, this was the heat of vaporization,
Mm-hmm.
and we used this to find Q to plug into this equation.
Got it.
So
Okay.
I can write that 1.17 kilojoules equals Q.
So we're finding Q by using that formula, right?
By
And
using
then,
the, should separate these. This
okay.
was this stuff over here. So we had to use, delta H of vaporization to get Q to plug into this equation, which we did over here.
Okay. Got it.
Okay. So to make sure I answer your question, make sure I understand your question so I can actually answer it, which is 100% on me. If I don't understand your question, that's on me. Are there any other questions on this one? We won't have a lot of problems that are sort of multi-step things being recombined, but this is one of the possibilities. Okay. So that's for heating and vaporization. Heating. For vaporization and condensation. We have similar things that we can do, though, with melting and freezing, right? So those are opposite processes. Something melts, the opposite of melting is freezing, vice versa. And then sublimation is kind of its own thing that we'll cover at the end. But all of these, whether it's vaporization, condensation, melting, freezing, or sublimation, are phase changes, right? So we're going from solid to liquid or liquid to gas, or in the case of sublimation, we're going from solid straight to gas. In our solids, when we're talking about melting, as that temperature of the solid increases, our thermal energy causes the molecules and atoms composing the solid to vibrate faster. And at the melting point, we've given enough thermal energy to those molecules for them to overcome the intermolecular forces that hold them at their stationary points and turns the solid into a liquid. Right? So they basically have enough energy to start moving around each other, whereas in a solid, they're just in fixed locations. So when ice melts, we've got water molecules break free from the solid structure to become liquid. And as long as ice and water are both present, the temperature will be 0 degrees C. Just like when we have water boiling, we have a combination of water and gas, steam, that will maintain 100 degrees C. So at each of these phase change sort of barriers, the temperature never changes. So this is where it's helpful to know that there's a separation between heat energy and temperature change. They're related, but they're not the same thing. So this is why also having ice in your drink, whether it's a soda, juice, whatever. There's some people who put ice in milk. I don't know why that bothers me so much. But it keeps your drink at 0 degrees C, which is why it stays cold so much longer than if you just had water by itself or whatever your beverage is. So again, just like boiling, a mixture of water and ice will always have a temperature of 0 degrees C, again at 1 atmosphere pressure. Only after all the ice is melted will additional heating raise the temperature of the liquid past 0 degrees C. So I don't know if you've noticed this phenomenon when you're, drinking a soda or something, but as soon as that ice is gone, it heats up in a hurry. So this should remind you of our previous heating curve that we saw. Again, we've got heat being added on our x-axis here, and then on our y-axis, we have the temperature, right, increasing as we move away from the origin. So this is our solid at the bottom. So ice can be colder than 0 degrees C, but as it heats up, it will reach that melting point. So this is ice. It'll reach that melting point, and then it'll level off because we have a combination of, I guess that cuts off the bottom there. I didn't realize it was cutting off the bottom. Oops. We have a combination of ice and water. That's going to stay 0 degrees C. And then after we've melted all of the ice, and we have only water, can we start heating again? So this is kind of analogous to, again, boiling water. We have some plateau where we level off, where additional heat does not increase the temperature, it's just going into breaking bonds or overcoming intermolecular forces. So we can add ice to a drink because, and again, like evaporation and condensation, melting is endothermic, right? So if we add the ice to the water is warmer than the ice. To melt that ice, you need to add heat to the ice. And here, again, to talk about it this way, ice is the system. So we have to put heat in to melt it, and that's endothermic. And the melting is endothermic because the energy required to because the energy is required to partially overcome the attractions between the molecules and set them free into a liquid state from their solid state. And then just like vaporization and condensation are opposites, freezing, the opposite of melting, is exothermic. And the heat is released when liquid freezes into a solid. So if you take, this is why you have to put water into the freezer to freeze it, because the freezer is actively removing heat from that box and pushing it actually outside of your freezer. So again, the system would be the water in this case, and we're removing heat from that water, which means it's an exothermic process. So as the water in your freezer turns into ice, it releases heat because freezing is exothermic. All right, the equation for this is going to be the same as well. It's just a unit conversion between the amount of water, ice, whatever, right, H2O. This is a unit conversion between the amount of energy it takes to melt it or freeze it and the amount of water that you have in moles. So delta H fusion is the amount of heat required to melt 1 mole of a solid. And again, the sign of our delta H fusion is tied to whether or not it's exothermic or endothermic. And this goes back to, oh shoot, which chapter was that? I think it was chapter 8, actually. But when we talked about endothermic and exothermic and quantities of heat that comes out of or goes into reactions, you can think of these like ATM transactions. So ATM, if you're adding money into it, right? If you have a positive number in your bank statement, that's endothermic. So our positive here, right? Delta H is positive because melting is endothermic. We have to add energy to the ice to melt it. I think it's just sort of speaking to the intuitiveness of this. It's easy, I think, to think of science and think, oh, it must be counterintuitive for some reason. In this case, it's not, right? You have to add heat to water or to ice to make it melt. So it's endothermic. Hopefully that helps. There can be a level of intuitiveness to this. So the opposite, though, is true if we are trying to, freeze water. So we're talking about melting, now we're freezing. And again, here, if we have a negative sign, that means we are removing heat from, or that heat is being removed from our system. Or again, if you want to think of it like a bank statement, right? We're moving money from your bank statement, you're going to have a negative value. So this is negative, it's exothermic. So delta H is negative because freezing. So it's negative because freezing is exothermic. Energy is given off as the water freezes. So this is why we put it into the freezer, because it's colder in the freezer than the water, and that removes heat from the water until it freezes. So just like with vaporization and condensation, we can use the heat of fusion to calculate the amount of energy, heat energy, required to melt a given amount of a solid. And we can use the heat of fusion as a conversion factor between the moles of a solid and the amount of heat required to melt them or freeze them. Works either way. Okay, so if we've got a 15.5 gram ice cube melts at 0 degrees C. Did we even, oh, we did get, okay. So this is going to be, sorry, I just looked at it, 6.02. And that's kilojoules per mole. We do another untitled poll here. Oh, here we go. Okay, so should the sign of our delta H fusion, delta H fusion, should be positive or negative? Because we're melting currently. Oh, it's 50-50. Well, it was 50-50. Now it's 45-58. 42-50. Sorry, 42-58. It changed as I was reading it. This is neck and neck. I know we just covered this stuff, so you haven't had any time to try and review it. I guess these answers are in now, but for those who haven't answered yet, if we're trying to melt this, are we trying to add heat to the ice, or are we trying to remove heat from the ice? If the ice is your bank account, are you trying to add money to it or remove money to it? Remove money to it? Okay, so 40%. Oh, one or two more votes. Only got 16 right now. All right, I'm going to close it right now. Okay, so I got 16 votes. More people said negative than said positive. This is, again, this is good. This is great. The Mentimeter stuff is going to be awesome when we can do it in lecture 2, because now I know I need to talk about this a little bit more. So we want to calculate the amount of heat absorbed when we melt this. So how do you melt? Oops, I don't want to do that. How do you melt ice? You have to heat it up. So that means if we have our system here, and this is the ice, we want to put heat into that, which means that delta H of fusion should be a positive 6.02 kilojoules. Yeah. Because it's going to require energy to melt. If we're freezing, if we're going the opposite direction, then we need to take heat out of it, and then we would have a negative. So this is also melting is also endothermic because it's more energy. So we're going to have our 15.5 grams of ice, right? So just solid H2O. And again, our first step here is going to be to convert this into moles. Because then we can use our 6.02 kilojoules per 1 mole to calculate the amount of energy there. So 15.5 times 6.02, positive 6.02, divided by 18.02 means that we'll need 5.18 kilojoules of heat to melt 15.5 grams of ice. It's actually a pretty decent amount of ice.
I have a question.
Yeah.
So whenever we're dealing with heat, or yeah, in this case, is it always going to be like, is it always going to end in kilojoules?
It will depend. So I think this is, again, that's a good question because it'll depend on what I ask for.
Okay.
So if I ask for the answer in kilojoules or joules, then, give it in whatever I ask for. And,
Oh, okay.
yeah. In this question where it doesn't say, whatever units is the most easy to calculate.
Mm-hmm.
So here, yeah, we ended with this unit conversion factor is in kilojoules. So just end with kilojoules. There's no reason to convert it to joules.
Okay.
Yeah. All right. Oh yeah, sorry, I keep bumping this microphone. All right, I had another one of these. Oh, that's the wrong one. Can we make this full screen? All right, so I don't know if we got a couple more in there maybe, but. All right, so now based on this graph, what state of matter is A? So it's either going to be solid, liquid, or gas. Oh, voting is closed. I need to open voting. Okay, you should be able to vote now. And again, this is on Mentimeter. All this stuff should be saved. Actually, I could zoom this in like this too. All right, so just looking at A, and let me know if it's not working. There we go. 2 solid, 1 liquid. I love how these graphs give like live feedback. Ooh, to liquid. Should have added a survey at the end too. Maybe I'll post a survey on Canvas or something. I feel like this is the sort of easiest way because like everybody in class, you can pull out your phones to do this. And it's just go to the website, type in the code. Aha! One person with the vote for gas. So the temperature that we have here on the x-axis, you can keep voting if you want. We're going to have more for B and C, of course. So keep that up. Don't close your the menti.com. So we've got here temperature, and this is for water, by the way. I'm sorry, maybe I should have mentioned that. This is all for water. So A here is below 0 degrees C. 0 degrees C is the freezing point of water. So this first leg is solid. Congratulations to you, 7. Thanks for voting, everyone. So this is water, or I mean solid water, ice. And then this next section here is our plateau for melting. So this is ice. Don't know why I did it like that. Ice, A is ice. Then this is a combination of ice plus water, right? Because that's our melting process. So throughout that range, we're adding energy, but the temperature doesn't increase until all of the ice is melted. Then we get past here. And what state of matter do we have after ice? Is ice also solid? Yeah, so now in this section, we've melted all of our ice, so now we just have liquid. And then we heat up again. Oh, wait a second, I just realized one of my slides wasn't in here. Oh, no, it's coming up. Okay, it's next. Yeah, so this is our liquid. Liquid water is B. And then when we get up to here, this is where we're boiling. So it actually takes a lot of energy to boil water. So this is a combination of water and steam. And then finally, whether by process of elimination or otherwise, what is C? Yeah. Don't have to spend too much time there. It's the last one. It's the only thing left. It's Steam. And not the game store. Yeah, so the heating curve for ice beginning at negative 25 degrees C and ending at 125 degrees C, the top of this curve, is not a nice, easy, straight line. It's not a curve. It's actually this very jagged looking thing. So we move from one thing to the other. And this is actually why we need a separate equation for these flat portions. Because remember, the other equation that we have for energy, relating energy and temperature, is that Q equals mc delta T. But when we're at one of these plateaus, let's just, say we're boiling. From here, which is, I don't know, let's say 15 kilojoules. That should be kilojoules, not kilojoules per mole. No, I guess it could be kilojoules per mole. Anyways, so if we're here at 15, all the way up to here, call it 55, it's close enough. Our temperature doesn't change. So if we wanted to calculate Q, let's just say we have 100 grams of water, and the C for water, the specific heat of water, is 4.184. And then delta T, though, which is equal again to T final minus T initial, would be 100 degrees minus 100 degrees C. So this would be 0 degrees C would be our change in temperature. So according to this equation, the amount of energy in there, well, we're not changing temperature, so there's no energy. So this would be 0, it would actually be joules. So Q equals MC delta T is a fine equation as long as you're in just one of the, as long as you only have one state of matter. And as long as you're not at a phase change, right? So if we're going from solid to liquid or liquid to gas, this Q equals MC delta T equation falls apart. Doesn't work anymore. Okay, so that's going to come into play here in our calculations when we're thinking about these. Actually, I think I have another Mentimeter quiz for this too. So I'm going to flop over to this. So if we're thinking about heating here, put this on the screen. If we're thinking about this problem, calculate the amount of heat in kilojoules needed to convert 1 mole of ice at negative 25 degrees C to water at 37 degrees C. What would you expect this graph to look like? So we've got A here where we're starting at, so these all start at negative 25, and they all end at, what is that, 37. But how we get there is a little different in each of them. 4 votes for A, 5 for A, 7 for A. Look at this. This is already way more people responding than ever respond in class. It's okay. I appreciate not wanting to respond because, like, I never responded in class when I was a student. Okay, so basically everybody who's voted is voting for A, which is great. Yeah, so it is A. So when we do this problem, remember, we have this flat section where we can't use Q equals MC delta T. We have to use this new equation. So really what we're going to get here, and this is kind of going back to math, is that this is a piecewise function. So we're actually going to have 3 different math problems based on the 3 different sections of this curve. So I'll go back over to this other one in a little more space. Oh, you know what I should have done? I'll just do that right now. Let's take this. All right, so with this in mind, oops. Let's put this over here. So with this curve in mind, you can see that we have negative 25 to 0. That's all going to be ice. And then above 0 degrees, that's water. So in this section, we're going to have ice plus water. So those are going to be the 3 sections of our graph that we work with. Anytime that our temperature changes, we can use Q equals MC delta T. And in fact, that's really the only thing that we can use based on the toolkit that we have. So again, Q equals MC delta T. So let's start there then at negative 25 degrees C. Let me do them over here. So we're going to have Q equals the mass of our water. So M here, let me do this. Q is heat in joules. M equals mass in grams. C equals specific heat in joules per gram degree C. And delta T is T final minus T initial, which is in degree C. Can actually be in Kelvin too, but Okay. So if we have 1 mole of ice, that means that we have really the molar mass of ice, right? So it's 18.02 grams. Grams of ice times the specific heat of ice, which is over here. And notice the specific heat of ice is different from the specific heat of water, liquid water. So it's going to be 2.09. That's joules per gram degree C. And then times our delta T. Oops. Need a little bit more space here. So our T initial is going to be negative 25 degrees C. What is our T final? I guess this one just go ahead and type in the chat. Or even just say it to yourself. So our T final here, I think there are two options that you could immediately jump to. One would be 37 degrees C, since that's the end of our graph here. But if you'll notice on the graph, this section does not go all the way up to 37. We just want to calculate, zoom all the way in on this, for this small leg from negative 27 up to 0. So our T final then is, for this section of the graph, is 0 degrees C. And remember, it's T final minus T initial, and in this case, T initial is negative. So our Q is going to equal 18.02 times 2.09 times a positive 25. Because if it's minus a negative, that makes it a positive number. So it's 941.545 joules. Actually, we'll switch colors here for this. Okay. So that was the first section of our graph. Now moving on to the second section of this graph, we want to calculate how much heat it takes to melt all of our ice. So this is the flat section here, where we have a combination of ice and water. This tells us how much energy it's going to take to get all of that ice into water. So here, instead of using Q equals MC delta T, we're going to use the fact that we have 1.00 moles of ice, and we can multiply that by our delta H of fusion, 6.02 kilojoules. This is also Q. Q just generically means heat energy. So it's 6.02 kilojoules per mole. So Q is going to be 6.02 kilojoules, because we only have 1 mole. So it's just 6.02. Then the final part of this graph is going to be heating up our water now. So it's this last section here. And we're going to use the same equation that we used for the ice warming up. And it's the same amount of water, H2O, so it's 8.02 grams. But now we need to use the specific heat of water, which is 4.184 joules per gram degree C. And now we're going to multiply by delta T. So we're heating up now. Our T final is that final temperature given in the question prompt of 37 degrees C. Minus our T initial, though. Again, we're just working with this one section at a time. So the start of this section, where we've got only water, liquid water, and we're warming that up, that starts at 0 degrees C. So 37 degrees C minus 0 degrees C is just going to be 37. So you do 18.02 times 4.184 times 37. And so Q is going to equal 2,789.64 joules. And again, I'm putting too many sig figs here because we're not done yet. So now we've calculated the amount of heat for each section on this graph. All right, we've got our, switch back to black here. We've got 2,789. This is in joules. We got 6.02, which is in kilojoules. And we have 941, which is in joules. So we need to convert these so that they're the same. And specifically in our question, it asks for kilojoules. So we're going to have 0.941545 kilojoules. I think that's supposed to be a capital J. The orange here, 6.02 kilojoules. I switch to the blue. It's going to be 2.78964 kilojoules. So if we want to know the amount of energy it takes to heat 1 mole of ice from negative 25 degrees C all the way up to 37 degrees C, which includes converting that ice into water, we just have to add all of these up for each section of this curve. So we'll take our 0.941545 plus 6.02 plus 2.78964. And that's going to give us 9 point, with the correct sig figs now, we only have 2 sig figs. This is going to be 9.8 kilojoules.
I have a question.
Yeah.
Where did the writing in the blue, where did you get 4.184?
Oh, I got that from the left over here.
Oh, okay. Thank you.
So that's the specific heat of water. So yeah, specific heat of ice is going to be different from the specific heat of water, or liquid, right? Solid water versus liquid water. And the specific heat of steam will be something else also.
I have a quick question on the like converting to kilojoules. So I know the previous problem we converted to kilojoules and we moved, I think it was 3 spaces to the right. So in this case, we moved
that was
the
going
left, right?
Yeah. So this was going from joules to kilojoules.
Uh-huh.
The other one was going from kilojoules to joules.
Okay, I see. Is there a conversion factor for that? Like you multiply or you divide by a specific number?
Yes. Yeah, so it's there's 1,000 joules in 1 kilojoule.
Got it.
Yeah. So multiplying by 1,000 is the same as moving the decimal place to the right 3 times. Dividing by 1,000 is the same as moving it to the left 3 times. Which is why scientific notation works. Any other questions for this? So this was just a problem going from going from solid water, ice at some temperature to water at another temperature. You could foresee a problem going all the way from ice at a temperature all the way up to steam at a temperature. So you'd have 1, 2, 3, 4, 5 equations to solve. I won't do that, but that is sort of the furthest extent that a problem like this could be taken to. Let's see here. Would like to get through a little bit more. Did I say in my announcement if we were going to go long tonight? I don't know if my voice can handle it at this point.
I think you did say that, yeah. Through the lab period, I think.
Yeah, into the lab a little bit. Okay. Yeah, let's actually do that. But let's take a break here, and then we'll see how long my voice holds out. So it's like a 5-minute break, and go to the bathroom. All right, it's been about 5 minutes. We'll get through a little bit more of this. Hopefully get just a little bit further ahead on each of these lectures. So at this point, we've talked about, vaporization, condensation, right? Going from liquid to gas, gas to liquid. We talked about melting, freezing, liquid to solid, solid to liquid. Those are sort of our normal ones. But we also have sublimation. So sometimes things go straight from a solid to a gas. So when we have a substance sublime, we have molecules that leave the surface of the solid, again, where they're held less tightly than the interior, and become gaseous. I think the most relatable example of this is dry ice, which you can go to a grocery store and buy dry ice. It's like $2 a pound, and they usually sell you like $7 or 7 pounds worth, so it's like $15 or so. And you have to handle it correctly, but it's not too dangerous, I should say. You can make some very fun punch for Halloween. It doesn't melt at atmospheric pressure, though, right? So if you buy dry ice, it's just slowly turning to a gas. And after about 24 hours, it's gone. And its temperature is negative 78 degrees C. So at that temperature, the CO2 molecules have enough energy to leave the surface of the dry ice and become gas. Dry ice, though, just does this fast enough that you can see it. All right, so we got solid dry ice, turns into a gas, happens rather quickly at room temperature. Regular ice actually also sublimes at temperatures below 0 degrees C. So in cold climates, which we don't really get snow around here, but ice or snow laying on the ground will just gradually disappear, even if the temperature remains below 0, even if it remains overcast and there's no sunlight shining directly on it. Also in your freezer, ice cubes will slowly become smaller, even though your freezer is always below 0 degrees C. It takes a long time for that to happen, but it happens. And ice also will sublime out of frozen foods. So the ice crystals that form in the bag, that's water that's sublimated out of the food and then redeposited. So deposition is the opposite of sublimation. That ice is then redeposited on the surface of the bag. And that's what causes freezer burn. That any liquid or ice in the freezer will also condense on the cooling coils at the back of the freezer. And that's why every once in a while you need to defrost your freezer, because otherwise the ice just continues and continues and continues to build up there. And it can stop your freezer from working, actually. So if you have a ton of ice built up in the back of your freezer, you should probably defrost it. Makes it less efficient, too. Costs you more in electricity. So if you can get colder and colder temperatures, like deep freezing, you could reduce that sublimation and preserve food longer. Okay. So those are basically changing phases, which is related to intermolecular forces. But intermolecular forces are at the core of all of those processes, right? We talked about why the temperature doesn't change when you're melting something or when you're boiling something. It's because all of the energy goes into overcoming those intermolecular forces. And things boil at different temperatures because of intermolecular forces. So these forces are electrostatic forces of attraction between molecules. The strength of the intermolecular forces determines the state. So something that's a solid is going to have stronger intermolecular forces than something that's a liquid or something that's a gas. Assuming that all things are at the same temperature. Stronger intermolecular forces tend to result in liquids or solids, and weak intermolecular forces tend to result in gases with low melting or boiling points. So the first force that we're going to talk about is also the weakest force, but it's the force that occurs between all things. Actually, I was looking this one up a little earlier. These dispersion forces, are also called London forces or London dispersion forces because they were proposed by Fritz, I think it was Fritz London, way back. Essentially, he proposed these dispersion forces as a reason that molecules like helium or xenon, these noble gases, right, as we talked about, they have full, well, actually helium only has two, but something like xenon would have a full valence shell, doesn't have any charges on it, but if you cool them enough, they will condense into liquids. And so these dispersion forces were how he proposed that they could exist as liquids, right? Because there has to be some force in between them that's causing them to stick together. So these dispersion forces are caused by fluctuations in the electron distribution within molecules or atoms. I frequently think of this as like one of those little plastic kiddie pools. And if you like bump one side in, all of the water will slosh to the other side momentarily. Now, if you imagine that you have a billion of those little kiddie pools all pushed up against each other, if you shove on one of those kiddie pools, it will shove into the other kiddie pools and cause this ripple effect, pushing all of the water out and away from that starting point. And essentially what's happening with London dispersion forces is that's what's happening with the electrons. As one molecule bumps into another, its electrons repel the electrons of that other molecule. And for just a brief instance, there are more electrons on one side of the atom than the other. So here's sort of a depiction of that. We have helium atoms in frame 1 here. So this is like 3 instances in time. Again, these electrons exist in orbitals, right? So like anywhere inside the sphere. But where they exist inside that sphere can be completely random, which means that sometimes they'll end up on the same side. And if they end up on the same side, you'll get this. This means slightly negative. That's a delta negative. And this is slightly positive. Because it's the electrons that are responsible for the negative charge in an atom, and it's the nucleus that's responsible for any positive charge. So if all of a sudden the electrons are all on one side, then you've got sort of the nucleus exposed on one side, the electrons on the other, and you get this difference in charge. And it acts like a magnet. So you got like kind of getting an instantaneous north pole and a south pole, which can cause an instantaneous north pole and south pole in another atom, or instantaneous dipole, rather, in other atoms. So you have these brief magnetic type attractions. So this is what I was talking about. If you get an instantaneous dipole in one of these atoms, it can induce a dipole in another atom, which can induce it in another. So any instance of a dipole can induce this in others, causing them to be very, very weakly attracted to each other. So the dispersion force occurs as neighboring atoms attract one another. The positive end of one instantaneous dipole attracts the negative end of another. The dipoles responsible for the dispersion force are transient, which means temporary, and really even briefly, very briefly temporary. They appear and disappear in response to fluctuations in electron clouds. So rather than just having this sea of kiddie pools all next to each other and pushing one of them, it's like you've got a bunch of them and they're all pushing back and forth on each other, causing that water to slosh around. If you think of the water as like the electrons, causing those electrons to slosh around and be unbalanced for brief moments. The magnitude of the dispersion force depends on how easily the electrons in the atom or molecule can be polarized in response to an instantaneous dipole, which depends on the size of the electron cloud. So this is again why I like this kiddie pool analogy. If you have a small kiddie pool, the water can't slosh very far, right, before it hits the other side of the kiddie pool. If you had a larger one of these plastic pools, that water could slosh more, right? Like it could all go over, more water could be on one side than on the other. The same thing happens with these electron clouds around atoms. So you might want to go back and review the sizes of atoms. I'll pull the periodic table. But the smaller atoms are going to be at the top right, fluorine, where the largest atom is going to be at the bottom left, which is like cesium, barium in that region. And when I say larger, I'm talking about the size of their electron cloud and the number of electrons that they have surrounding them, which can kind of squish and move around. So it's not the only thing determining the magnitude of the dispersion force, but if you're comparing similar things, you can use that, right? So bigger atoms, more molar mass means more protons, means more electrons, which means that they have stronger dispersion forces. So if we look at these noble gases and compare their boiling points, we can see that as our molecules get larger, the boiling point also gets higher. And remember, the boiling point is related to the amount of energy it takes to overcome the intermolecular forces. So a higher boiling point means it requires more energy. So xenon here has a boiling point of 165 Kelvin, which is like negative 109 Celsius. Very, very cold still. It boils. But these are also getting larger as we go down, which means more electrons, which means more sloshing of electrons, and stronger dispersion forces. We're going to get through dispersion forces and then call it, because my voice is about to give out. All right, I had a Menti quiz for this one too. So which hydrocarbon has the higher boiling point? Actually, I'll draw these for you as well. They're sort of skeletal structures. Oops. Excuse me. Yeah, so again, you just if you're thinking about the size of these things, right, because that's really the only thing we've talked about so far with dispersion forces, the bigger it is, the stronger the London dispersion forces, and that'll have some effect on the boiling point as well. Oh, the screen's freaking out a little bit. Oh, it doesn't show up on here. That's good. Yeah, so the C2H6, which is ethane, is going to have a higher boiling point because it's a larger molecule and it's a similar type of molecule. That these are both similar types of molecules. So this will have the higher boiling point. And that's because it has stronger, I won't call them London, we just dispersion forces. Okay, that was the last slide of that. So that was dispersion forces, and we're going to continue to talk about these in terms of increasing strength, right? So next is going to be dipole-dipole force. If you're not doing this already, I recommend reading the slides ahead of time so you come to class and you're sort of a little more prepared for what's going on. Actually, maybe we'll just have a quiz next week when we're back in person. If I don't post anything about a quiz, don't expect a quiz on Wednesday. Are there any questions about dispersion forces, about anything else at this point?